Welcome back. We continue our study of chapter 3 and we move to section 3.2 about connectedness and locally constant maps. Okay, so let us recall one important consequence of the classical mean value theorem, version 1.0. And this is something that you use all the time. If f is a differentiable function on an open interval I of r, and if the derivative of f is 0, then f is constant. Okay, so you use that all the time. Why this is true? This is a consequence of the mean value theorem, as we said, because if you take two arbitrary points a, b, and I, then when we apply the mean value theorem, we can write f of b minus f of a equal f prime of c times b minus a. But if f prime vanishes, then f prime of c is 0, and therefore you get f of b minus f of a equals 0, and therefore f of b equal f of a. And this is true for all a and b, and this precisely means that f is constant. Okay, consider, however, this example. Consider the function f defines on R without 0 by arctangent x plus arctangent of 1 over x. Of course, f is differentiable, and when we compute the derivative, we get 1 over 1 plus x squared plus minus 1 over x squared, which is the derivative of 1 over x, divided by 1. This is the chain rule again, so when we simplify, you get 0. However, f of 1 is arctangent 1 plus arctangent 1, which is pi over 4 plus pi over 4, so it's pi over 2. And f of minus 1, this is minus 1 here, is minus pi over 4 plus minus pi over 4, which is minus pi over 2. So what's wrong with that? Why we didn't find a constant, although f prime is 0? I want you to pause the video and think a little bit of this riddle. I'm sure you will find what's wrong. Okay, there is a very important assumption here. I is an open interval. Okay, because in order to apply the mean value theorem, we have to work on an interval. Okay, R without 0 is not an interval. So this is why this conclusion does not work. This corollary does not work. However, if we restrict f to the positive real numbers, 0 plus infinity, then actually f is constant on 0 plus infinity and it's constant on minus infinity 0 as well. Okay, so we say here that f is locally constant. Okay. Now, as we said, there are at least 3 generalizations of the notion of interval in higher dimensions. We saw already the notion of convexity. And now we shall deal with two more general generalizations, which are connectedness and path connectedness. Okay. So, in general, a topological space is said to be connected if the only closed and open subsets of X are only the empty set and the whole space. So these are, in any topological space, the empty set and the whole space are closed and open at the same time, and we can call them clopen. Now, not all topological, so some topological spaces have this property that the only clopen subsets are the empty set and X, and such we call such spaces connected. Okay, so, and this is equivalent to the following fact: we cannot write X as a union, a disjoint union of two open non-empty closed sets or open sets, same thing. Okay, so if you like, one way of thinking of connectedness in intuitive ways, connected set is mainly a one-piece set. Okay, so unlike R without 0, R without 0 is not connected. Okay, because it can be written as the union, as a disjoint union of two open, non-empty, and disjoint sets. Okay. However, all intervals of R are connected, and conversely. So in R, there's an equivalence between connected and interval, and convex as well. However, the situation is not does not hold in higher dimensions. So this now I will give some. So we have now three notions: connectedness, and I will now define path connectedness. So a path in a topological space is just a continuous map of some interval alpha beta of R into the space. Okay, and we can always take alpha beta to be 0, 1 because alpha beta is homomorphic to the interval 0, 1. Of course, when I write this, I always assume alpha is less than beta. So gamma alpha and gamma beta, this is alpha and beta, are called the endpoints of gamma. Okay, and we say that the space X is path connected if any 2 points of X can be joined by a path in X. Okay, so there is a continuous map from an interval alpha beta to X such that gamma of alpha equal A and gamma of beta equal B. So this is gamma of alpha, gamma of beta. Okay, so now alpha and beta are real numbers and A and B are points in a topological space. In Math 2201, we proved that path connectedness implies connectedness, but the converse is not true. However, you probably proved this in the next semester of second year. When we have an open subset U of a normal space, then we have an equivalence between U connected, U path connected, and even more, any 2 points of U can be joined by a polygonal path. Now, what is a polygonal path, or a broken line, if you like? Should be clear. It's a concatenation or juxtaposition of straight line segment. Okay, so this is a particular kind. A polygonal path is a particular kind of a path. Okay, it's piecewise linear, if you like. Okay, now I'm not going to prove this, but the proof is very important actually. In principle, you study it in second year, and you can find it in the book of Carton. So it should be clear that 3 implies 2 and 2 implies 1. So just have to prove that 1 implies 3. To prove that 1 implies 3, we use what we call a connectedness argument. It's very, very important, and we shall revisit this again. So what do? We fix a point A in U, and we consider the set capital A of all points of U that can be joined to A by a polygonal line or polygonal path. Then we prove that A is not empty. Of course, it's not empty because it contains small a. A can be joined to itself by the constant path. And it's open and closed. Okay, so now connectedness, since U is connected, then by definition, this implies that A is equal to U, and therefore all points of U can be joined to small a by a polygonal path. But since A was arbitrary, this means that any 2 points of U can be joined by a polygonal path. Okay, so you can, it's a very good exercise. If you didn't see the proof before, try to prove that A is both open and closed. Okay, and when you do this as an exercise, try to generalize this to an arbitrary topological space. But this is not true for any topological space. You have to put some assumptions on the topological space X in order that every open and connected set is path connected as well. So it's the converse. Okay, we have to put an extra assumption because otherwise you can give a counterexample. Okay, so we have the following implications. Convex implies path connected implies connected, and of course the reverse inclusions in general are not true. However, we proved that connected implies path connected if the set is open in a normal space. Now, of course, path connected does not imply convexity, of course, because you can just draw a figure. Okay. Now, what is the relation between connectedness and locally constant maps and zero derivatives? So this is what we are trying to do to clarify now. A locally constant map defined on a subset U of a norm space, and that takes values in another norm space, say that it's locally constant if every neighborhood of U has, if every point of U has a neighborhood on which f is constant. So the function arctangent x plus arctangent 1 over x actually is locally constant. But this is very similar to this other function, which just takes two values, 1 and -1, 1 if x is positive and -1 if x is negative. Then this is locally constant, because if you take any neighborhood of any point in R without 0, then it's either positive or negative. It's positive. If it's positive, then there is an interval of center x contained in the positive numbers, and therefore the value of f will be 1. And similarly, by symmetry, same thing for if f is negative. Okay, so this is an example of a locally constant map, but which is not globally constant. Okay, and now we clarify the relation between connectedness and local constancy. If we have a map from a subset of a norm space into another norm space, if f is locally constant and the domain of f is connected, then actually f is constant. This is an important illustration of the use of topology in analysis. Local constancy is a local property, okay, and connectedness is a topological property. So what this theorem is saying that if f is locally constant and the domain of U has some topological property, then f is globally constant. So this illustrates the fact that topology helps us in moving from a local property to a global property. By the way, let me open a parenthesis. We have other situations. For example, continuity is also a local property. So if you have, if f is continuous on a compact space, then it's uniformly equicontinuous. So equicontinuity is a global property, unlike continuity, which is local in nature. So this is another example where topology permits us to go from the local to the global. And the proof here of this theorem is very easy, actually. So first, you have to check that a locally constant map is automatically continuous. So you don't need to assume continuity. Why? Try to prove that. Just go back to the definition. Because if it's constant around a neighbor or around a point, then the difference will be 0. So it can be made less than any positive number epsilon I. Now, pick a point small a in U and consider the set of all points in U whose image is equal to f of a. Then what can you say about this set capital A? First of all, it's not empty because it contains small a. Second thing, we can write A as the inverse image of f of the singleton fa. But in metric spaces, singletons are closed. So A is the inverse image of a closed set under a continuous map, so it's closed. And third thing that you have to check is that local constancy implies that A is open. How do you prove that? You take a point x0 in A. Then there is a neighborhood of x0 on which f is constant, and therefore f takes the value for every x in that neighborhood, f of x equal f of x0, which is just f of a. So very easy. Now, since U is connected, then we have to deduce that A equal to U, and therefore all x in U have the same image under f. So f is constant. Okay. So compare with this example. Okay, this is locally constant but not constant because R without 0 is not connected. Now, to go further, if you want to dig deeper, this is a useful exercise. It's optional, actually, if you like general topology. If you want to generalize this theorem to maps between topological spaces, we have to put some condition on the target space. Okay, I'm sure that you guessed what is this condition. It's not true in any topological space. You have to put some condition on Y. So try to discover what is this condition. Okay. Now, as a corollary, so if you have, again, two normal spaces E and F and an open subset U of E, note that here I didn't need the assumption that U is open. I never used it. So U can be arbitrary here. But now I need the assumption of openness. You'll see why. Then F is locally constant if and only if F is constant on the connected components of U. What are the connected components of U? There are several characterizations. A connected component is a maximal connected subset of U, which means that it cannot be contained in a bigger, strictly bigger connected set. It's also an equivalence class for the relation X equivalent to Y if X and Y belong to the same connected set. Also, the connected component containing a point is the biggest connected set containing that. So all these three are equivalent. Okay, so just to be simple, what are the connected components of R without zero? There are two: minus infinity zero open union and zero infinity open. Okay. Okay, so I have to prove two implications here. Suppose first that F is locally constant. Then by the previous theorem, it is constant on every connected subset of U. And in particular, it's constant on the connected components of U, because connected components are connected subsets, particularly. But in some sense, they are maximal elements with respect to inclusion, of course. Conversely, suppose that F is constant on every connected component of U. We want to prove that X is locally constant. So pick an element X in U, and let's see, denote the connected component containing X, which by definition is the biggest connected set containing X. Biggest connected subset of U, of course, because we are working in U. Okay, it's the union of all connected subsets containing X. Okay. This is the component. Now, since U is open, here I'm using this fact, then there is a ball of center X contained in U. Now, the ball of center X and the radius R is a convex set, as you know, and therefore it's connected. And every connected set is contained in some component. So it's contained in C, because C is, so BXR is a connected set containing X, and C is the biggest connected set containing X. Therefore, C contains BXR. Okay, so now, since F is constant on C, because by assumption F is constant on every component, then F is constant on the ball. Therefore, F is, since X was arbitrary, F is constant, is locally constant. Okay, so this concludes the reverse implication. Now, the last argument here shows actually that the connected components of U are open. Okay, because we can find a ball contained in them. Now, as an optional exercise, try to generalize this to maps between topological spaces. The result is not true for arbitrary topological spaces, because you can give counterexamples actually. However, if you put some extra assumptions on X and Y, this corollary will hold actually. So you have to put now a condition on X and the condition on Y in order for that to be true. Okay. And now I will end with the relation between local constancy and the vanishing of the derivative. So once again, if we have a map from an open subset of a norm space into another norm space, then F prime is 0 if and only if F is locally constant. Okay. Okay, so I have to prove two implications. Of course, if F is locally constant, then the derivative is 0 if you just go back to the definition, because if you just write f of x plus h minus f of x minus 0 h, this is 0. So of course it's a small o of h. So this proves actually two things. It proves that f is differentiable and the derivative vanishes. Okay, but here the converse is interesting. This is a consequence of the general mean value theorem version 3.1. Okay, so pick a point x in U. Since U is open, there exists a ball of center x contained in U. And now pick 2 points in this ball, A and B. Since B is convex, we can apply the mean value theorem version 3.1. Okay, so we can write f of b minus f of a is less or equal than the maximum of the derivative, which is 0 times b minus a. So it's 0. And therefore f of b equal f of a, and therefore f is constant on bxr. So this proves that f is locally constant. Okay, so this is one implication. The other one was, I did it orally. Local constancy implies derivative 0. Okay, and the last corollary, if U is differentiable on a connected set, open connected set, and the derivative vanishes, then f is constant, actually. And this is the general theorem that you are familiar with from high school. Okay, so we have a topological condition, which is just connectedness, that permits me to say that if the derivative is 0, then f is constant. It's very important, and you use it all the time to compute integrals or solve differential equations. Whenever you have 0 derivative, you conclude that f is constant, but there is a very important assumption which generalizes the notion of interval, and it's called connectedness. Okay, so one piece. So if, in simple words, if the domain of differentiability of f is one piece, then f is constant. If it's not connected, we saw that the result may be wrong. Okay. So this concludes the video in section 3.2 that relates connectedness, local constancy, and vanishing of the derivative. So thank you for your attention, and see you next time.